You know how life is full of problems where you have multiple, sometimes conflicting rules to follow? Well, what if you could actually see all the possible right answers in a single picture? Today, that's exactly what we're doing. We're exploring how graphing systems of inequalities creates that picture, a solution zone for making tough decisions.
I mean, think about it. You've got a budget for a party, or maybe you only have so much time in the day, or certain ingredients you can use for a recipe. We're always balancing these limits. The trick isn't just finding one answer that works, it's understanding all the options you have. And that's what we're going to map out today.
So, to make this super clear, we're going to follow a real-world problem. A photographer named Christy, who's trying to figure out what photos to sell at a fair. It's the perfect way to see how we can turn a bunch of constraints into a clear, visual game plan.
Okay, here's the plan. We'll start with what makes inequalities different. Then we'll get into how to draw the boundary line and shade in the right area. After that, we'll see the magic happen when these areas overlap, and finally, we'll put it all together to solve Christy's problem.
All right, part one, more than just equal. Let's just quickly get on the same page about what an inequality really is.
So, you know how an equation like y equals x plus 2 is super specific? It's like a tightrope. All the answers are right there on that one single line. But an inequality? Oh, that's a whole different ballgame. Something like y less than or equal to x plus 2 isn't just the line, it's the entire field on one side of it. It's a whole zone of solutions. And that's the big idea for today.
Now, what happens when you've got more than one of these conditions at the same time? That's what we call a system. And the key, the absolute most important thing, is that we're looking for the points that make every single one of those inequalities true all at the same time. All right, section 2, drawing the line. The very first step is to draw the line that acts as the fence or the boundary for our solution zone.
Okay, this is actually pretty cool. The line itself tells you a story. A solid line means the boundary is part of the solution. It's like the door is closed and you can stand right on the doorstep. But a dashed line, that's more like an invisible fence. You can get right up to it, but you can't actually be on it. It's for a strict less than or greater than situation.
Okay, section 3, picking a side. Once we have our boundary line drawn, we've got to figure out which side of the fence is our solution zone.
So how do you know which side to shade? Here's the easiest trick in the book. Just pick a super simple point that's not on the line. Honestly, 0, 0 is your best friend here. Plug it into the inequality. If it works, if it makes a true statement, you shade that whole side. If it's false, you just shade the other side. Easy, right? It's a foolproof check every single time. All right, part 4, where solutions overlap. This is where it all comes together. We're going to put multiple inequalities on the same graph to find the true solution. Okay, now for the magic. Imagine you have 2 of those old-school transparent sheets. You shade the solution for your first inequality on one sheet, maybe in red. Then you shade the solution for the second one on another sheet, say in blue. When you lay them on top of each other, what happens? The spot where the red and blue overlap turns purple, right? That purple area, that double shaded zone, that's our solution to the whole system. Let's look at this one. First, you'd handle x minus y greater than 3. You draw its boundary line, dashed, of course, and then test a point to figure out which side to shade in red. Then, on the very same graph, you do the whole dance again for y less than 1/2 x plus 4 and shade its solution in blue. And boom, you get this. See that darker area where the 2 colors overlap? That is our golden ticket. Any, and I mean any, point you pick from inside that zone will solve both of our inequalities at the exact same time. Pretty powerful stuff. Okay, section 5, solving real-world problems. Let's get back to our photographer, Christy, and use this new skill to solve her problem at the fair. So, let's remember Christy's situation. She has 2 big rules she has to follow. First, a quantity goal. She's got to have at least 25 photos total. Second, a money rule. She can't spend more than $200 on prints. She has to find a plan that follows both rules. So, here is a question. Could she display 20 small photos and 10 large ones? Sure, we could just plug the numbers in and do the math. But if we graph it, we not only answer this question, but we also see every other possible combination that works, all at a glance. And look what happens when we graph her 2 rules. We find that sweet spot where the shading overlaps, and then we just look for our point, 20, 10. And there it is, sitting right inside the solution zone. It works.
So is it possible? Yes, the graph gives us that instant answer. But what's even better is that Christy can now see all these other points inside that zone. It gives her a ton of options and flexibility.
And you know, the really cool thing about this whole idea is that it doesn't just stop with straight lines. That's right. As soon as you start seeing squared terms in your equations, you're not dealing with lines anymore. You get these beautiful curves called parabolas. So the boundary might be a curve now, but the basic idea is exactly the same. The solution is still a shaded region. It's either everything inside the curve or everything outside of it. This concept is huge. It's used in everything from economics to engineering to design complex things.
So that brings me to a final question for you. Think about your own life. Maybe it's planning a workout routine with time and intensity limits, or even figuring out a gaming strategy. What real-world problem could you map out, just like this, to find your perfect solution zone?